is Ananda Rico from Bioprocess Engineering. My student number is 2306171032.
Hello everyone, my name is Zavier from Bioprocess Engineering.
Hello everyone, my name is PUTRA PRAYATA. My NPM is 2306552.
Today we'll be talking about sulfonation of benzene. Sulfonation of benzene involves adding a sulfonic acid group to the benzene ring. This process typically occurs by treating benzene with concentrated sulfuric acid and a catalyst like sulfur trioxide. The reaction proceeds through an electrophilic aromatic substitution mechanism where the sulfuric acid acts as an electrophile, attacking the benzene ring to replace the hydrogen atom with the sulfonic acid group. The sulfonation of benzene is an electrophilic aromatic substitution reaction that involves the addition of sulfonic acid group to the benzene ring, typically carried out with fuming sulfuric acid with three main steps. The first step is the p electron of the aromatic acts as a nucleophile, attacking the electrophilic S, pushing charge out onto an electronegative O atom, destroying the aromaticity, giving the cyclohexadienyl cation intermediate. Loss of the proton from the sp3C bearing the sulfonyl group reforms the C double bond and the aromatic system. Protonation of the conjugate base of the sulfonic acid by sulfuric acid produces the sulfonic acid. Desulfonation of benzene refers to the addition of two sulfonic acid groups to the benzene ring. This is achieved by further treating the sulfonated benzene, which already has one sulfonic acid group attached, with more sulfuric acid and heat. The second sulfonic acid group is added to another carbon atom on the benzene ring, resulting in a benzene molecule with two sulfonic acid groups attached. Both sulfonation and desulfonation of benzene are important processes in organic chemistry for synthesizing compounds with specific functional groups attached to the benzene ring, which can alter the properties and reactivity.
So there's Friedel-Crafts alkylation. So Friedel-Crafts alkylation is a method used to add alkyl groups into the aromatic rings. It involves creating an alkyl halide with an aromatic compound in the presence of a Lewis acid catalyst. The catalyst activates the alkyl halide, forming a carbocation intermediate which then reacts with the aromatic rings. This leads to the formation of a new carbon-carbon bond between the alkyl groups and the aromatic rings. The Lewis acid catalyst is regenerated in the process. So that's the general equation. And for the steps is the visualization, but basically the steps to do this reaction is the alkyl halide will be activated once it is reacted with the Lewis acid catalyst. And after that, the activated alkyl halide will break apart and then leave positively charged carbon or the carbocation. And then the carbocation sticks into the aromatic rings, which has a lot of electrons. And then after they stick, it will form a new carbon-carbon bond. It'll add the alkyl group to the aromatic ring. Next. And after alkylation, there's also Friedel-Crafts acylation. So Friedel-Crafts acylation is a chemical reaction used to add an acyl group into an aromatic ring. It involves the reaction of an acyl halide with an aromatic compound in the presence of a Lewis acid catalyst. The acyl halide is activated by the catalyst, forming an acylium ion, which then reacts with the aromatic rings to form the acylated aromatic product. So it is similar to the alkylation, but the thing that is added is the acyl group. So there's the general equation and the visualization for the steps. And for the steps itself is similar. The acyl halide got activated by the Lewis acid catalyst, and then acylium ion got formed, which is positively charged, and then will be also attached to oxygen atom, and then it will react with the aromatic rings, and the acylium ion adds to the ring, form a new carbon-carbon bond, and then the acylated aromatic product will be formed. Next. But there's also limitation of the Friedel-Crafts reactions, both the alkylation and the acylation. The first one is when the carbocation formed from an alkyl halide, alkene, or alcohol, it can rearrange to a more stable carbocation, and then the major product obtained is usually from the more stable carbocation. Second one, the vinyl halides and the aryl halides do not react in Friedel-Crafts alkylation because the carbocation derived are highly unstable. And then the Friedel-Crafts reaction usually give poor yields when powerful electron withdrawing groups are present on the aromatic ring due to the instability of complex. When the ring bears an H2, an HR, or an R2 group, these groups are changed into powerful electron withdrawing groups by the Lewis acid catalyst so that those groups do not give Friedel-Crafts reaction. And the last one is another limitation of Friedel-Crafts alkylation arise because polyalkylation as an alkyl substitute benzene is more reactive than benzene itself. However, no polyacylation takes place.
Okay, so for the next one is the effect of substituents on reactivity and orientation. So, when planning synthesis involving substituted benzenes, predicting which position on the ring will be most reactive is crucial. So there are three main challenges that we need to be concerned on. The first one is confirming the structure of the formed isomers. The second one is determining the proportions of each isomer in the product mixture. And the last one is measuring the reactivity of the compound being substituted compared to a standard substance, typically benzene. And it is often possible to identify the isomers by converting them to compounds of known structure. For example, trifluoromethylbenzene on nitration gives only one product, which has been shown to be 3-nitro derivative by conversion to the known 3-nitrobenzoic acid by concentrated sulfuric acid. And for the structure, there is a picture down below. Next. Okay, now for the theory of orientation. So the theory of orientation, there are two groups. There are activating groups and deactivating group. So for the activating group, atoms or groups that makes the benzene molecule more reactive by increasing the ring's electron density are called activating groups. And then activating groups serve as ortho-para directors when they are attached to a benzene ring, meaning that they are direct incoming electrophile to the ortho or para positions. And the last one is activating groups increases the rate of reaction relative to H, while the deactivating group, an atom or group that makes the benzene molecule less reactive by removing electron density from the ring, acts as a deactivating group. And the deactivating groups direct incoming electrophiles to the meta position. Activating groups decreases the rate of reaction relative to H. Next. So for the theory of orientation, this is a little bit of a summary. So the activating group increase the rate of reaction relative to H, while the deactivating groups decrease the rate of reaction relative to H. Activating groups tend to donate electron density to the ring, while deactivating groups tend to withdraw electron density to the ring. And there are a couple of strongly activating for activating groups and deactivating groups. So for the strongly activating, there's alkoxide and amine, while the strongly deactivating is cyano, nitro, and haloalkyl.
Today I am here to talk about orientation based on sigma complex stability. First of all, chemistry uses a matrix called sigma complex stability, or SS, to quantify how reactive a chemical reaction is, particularly when aromatic compound nucleophilic substitution reaction are involved. It measures the energy shift that occurs when a nucleophile binds to an aromatic ring and forms an intermediate sigma complex. The energy of the sigma complex is subtracted from the total energies of the aromatic molecule and the nucleophile to determine this energy change, SS. That SS sheds light of these reaction stability and activity. So to talk about this is first of all is the concept that we use, which is this is the concept of sigma complex stability is used to quantify reactivity in certain chemical reaction, particularly in the context of nucleophilic substitution that I just said, and the sigma stability, which is SS, and is theoretical quantity that represents the energy change associated with the formation of the intermediate sigma complex, which occurs when a nucleophile attached, which is like this part is like attached, like there's this agent that attaches such as. Then we're just gonna there's an example for clarity, such as wait, to one of them is nitration benzene, which in the nitration of benzene, a natrium ion NO2 plus acts as an electrophile. The benzene ring donates a pair of hot electrons to form a bond with natrium ion, resulting in a formation of a sigma complex, which we just saw in the picture. Next is the sigma complex is not as stable as the original benzene molecules due to disruption of the aromaticity. So aromaticity is kind of a huge role in it. So like yeah. However, it stabilized to some extent. So it stabilized, it balanced out in some extent by the localization of the positive charge over the ring. This ring. And next then the more stable the sigma complex is, the faster the reaction will proceed. So probably if your sigma complex is very stable, probably the reaction will not be seen at all, or I don't know. Next is Friedel-Crafts alkylation, which is I think it's yeah, it's here, but like it's for my friend. It's one of the practical examples. The first example, which is nitration of benzene, and the second is Friedel-Crafts alkylation. In these both examples, the orientation of substitutes on the aromatic ring can be influenced by the stability of the sigma complex. For instance, electron donating groups can stabilize the sigma complex and direct the incoming electrophile to ortho and para position. On the other hand, electron withdrawing groups destabilize the sigma complex and direct the incoming electrophile to the meta position, which goes back. This example illustrates how the concept of complex stability can be used to understand and predict the outcomes of electrophile aromatic substitution reaction. Okay, so back to the thing. Wait. So we're just gonna jump to what is para and wait. Okay, wait a bit, guys. It's kind of laggy. So next is, well, we already talked about the orientation based on sigma complex stability. The next is the ring. Ooh, exciting. So the ring, adeninium ion or a Wieland intermediate is a sigma complex, is a reactive intermediate that arises in electrophilic aromatic substitution process. It is often referred to as an aluminum ion or a Wieland intermediate. The smallest example of aluminum ion is benzone ion, which is protonated benzene. It is a cyclohexadiene caution. So, which is that, that's that. And in some cases, sigma complexes can be stabilized through the formation of zwitterionic combination of Meissenheimer and Wieland complexes. These anionic sigma complexes or Meissenheimer complexes are more stable than uranium ions or this called Wieland intermediates and can be isolated more easily and probably quickly. Next is more about this is like the stability of a sigma complex can influence the orientation of substituents in aromatic compounds, as well as the overall reactivity of the system. For example, a complex electrophile can contribute to a stability of uranium ions, which can in turn affect the course of reaction, which can proceed it quickly and proceed it slowly, whatever. Also, in summary of all of these stuff, which is one of these is orientation based on sigma, and the uranium ion is it provides a theoretical framework for understanding and predicting the reactivity of aromatic compounds in nucleophilic substitution reaction. By quantifying the energy change associated with the formation of the sigma complex, it is possible to gain insight into the factors that influence the stability of these complexes and their role in each chemical reaction. So there's some cases, probably this is not needed, but I'm just gonna include it. There's an illustration of cases. Let's consider two specific examples, right? About electrophilic aromatic substitution, the nitration of benzene, and the halogenation of benzene, which is kind of easy. I think it's kind of easy. I don't know. I think it's hard. Okay, so the first of all, nitration of benzene. In the nitration of benzene, the electrophile is the deuterium ion, NO2 plus. And the benzene ring, like a ring, donates a pair of electrons to form a bond with the nitronium ion, creating a sigma complex, which is like here, this. Sorry. The sigma complex is not stable as its original benzene molecule due to the disruption of the aromaticity. However, it is stabilized to some extent, just by extent, by the delocalization of the positive charge over the ring. The more stable the sigma complex is, which is, yeah, it goes faster. The better, the more stable, the faster, the more unstable, the slower. That's it. Now, the second of all is halogenation of benzene. A halogen such as C12 or Br2 reacts with the benzene ring in the presence of a Lewis acid catalyst such as F iron and C13 or iron and brominium 3. The Lewis acid is actually steel and iron and chlorine 3 or iron and brominium 3. The Lewis acid first reacts with the halogen to form a more electrophilic species. This electrophile then reacts with the benzene ring to form a sigma complex. The stability of this sigma complex will influence the rate of reaction, as said. Now, next is, in this both examples, the orientation of the substituents of the aromatic ring can be influenced by the stability of the sigma complex. For instance, electron donating groups can stabilize the sigma complex and direct the incoming electrophile out to the ortho and para position. On the other hand, electron withdrawing groups destabilize the sigma complex and direct the incoming electrophile to the meta position. This example illustrates how the concept of sigma stability can be used to understand and predict all of these reactions. Okay. So these is, I will tell you all the sites and like, wait. Sorry. So there's a specific cases. There is nitration of toluene, which will be next, I think. I forgot the thing. And there's bromination of nitrobenzene, which is probably going to be like very later. So that's it for my.
Okay, for the first question, in the solvenation of benzene, the active electrophilic species is next. Okay, for this question, there's 3 steps. First step is the 2 molecules of sulfuric acid will react, where one will act as acid, and the one will act as a base to form conjugate acid and the base of sulfuric acid. So Okay, so this is for the first step, and the second step is the H2O molecules gets removed from the conjugate acid of sulfuric acid to form SO3H plus. If we make the structure, then it will look like this. Wait, I forgot this one. And for the last step, the third step is the H plus gets removed from the SO3H plus to form H3O plus and SO3. And it will look like this. And that's for the first question. On to the next question.
Okay, maybe wait. Okay. So for the second question is for a Friedel-Crafts alkylation process, benzene and propyl chloride with aluminum chloride as a catalyst is used to synthesize isopropyl benzene. However, after the reaction, the yield is lower than expected. Identify the most likely reason for the low yield in this reaction and suggest a modification to improve the yield. Choose for the answer itself is propyl chloride is prone to rearrangement to a more stable carbocation during the reaction, leading to isomerization and a mixture of products. For the explanation, in Friedel-Crafts alkylation, alkyl halides can rearrange to form more stable carbocations. For propyl chloride, a rearrangement can occur, forming a secondary carbocation or isopropylcation, which is more stable than the primary carbocation. This rearrangement can lead to a variety of products rather than the desired isopropyl benzene alone that reduce the yield. To improve the yield, we can use an alkylating agent that forms a more stable carbocation without rearrangement, such as tert-butyl chloride